It is 5:47 a.m. on the Columbia River Plateau. The temperature in this part of eastern Washington in January of 1936 sits at 11 degrees Fahrenheit. The canyon walls above the construction site are gray and frozen. The Columbia River moves below, dark, fast, indifferent to everything happening on its banks. And on its banks, 7,000 men are already at work. The Grand Coulee Dam is rising out of the basalt of this canyon. When finished, it will be the largest concrete structure in the Western Hemisphere, larger than the Great Pyramid of Giza by volume, 3 times the mass of Hoover Dam, a structure so immense that engineers working its lower forming galleries will later describe feeling the weight of it through the soles of their boots, a pressure that doesn't come from sound or air, but from the rock itself, from something geological, something that has been building for longer than men have been building anything. The machine responsible for feeding this structure runs on steel rails spiked directly into that basalt. It is a Baldwin 210-2 compound steam locomotive, built in Philadelphia in 1929. Its operating weight is 432,000 pounds. Its boiler runs at a working pressure of 220 pounds per square inch, producing a tractive effort at the rim of its driving wheels of 86,000 pounds. It can haul 42 loaded aggregate cars up a 2% grade at walking pace without slipping. At full load, its fireman shovels coal at a rate of 1 ton every 40 minutes. The exhaust from its stack at that load is visible from across the canyon, a column of black and gray that rises above the rim rock before the wind cuts it apart. It is, by almost every measure available in 1936, exactly the right machine for this job, until the morning it stops moving, not from mechanical failure, not from operator error. The locomotive stops because the track beneath it has dropped 6.5 inches, and the track has dropped because the basalt bedrock beneath that track, volcanic rock, laid down 16 million years ago at the end of the Miocene, rated by Bureau of Reclamation field engineers at 28,000 pounds per square inch in unconfined compression, has given way, not cracked, not sheared, compressed, under the 72,100-pound axle load of this machine's 8-paired driving wheels. The canyon floor itself has moved. The foreman on the night shift, a 22-year Bureau veteran named Earl Cushman, writes in his incident log that morning, "Rock does not do this. He is wrong. But understanding why requires understanding everything that came before that track dropped. The Bureau of Reclamation begins excavating the Grand Coulee Foundation in the summer of 1934. Drag lines and clamshell buckets strip the river, alluvium and Pleistocene gravels from the canyon floor. What they expose beneath is not uniformly promising. The basalt is sound in places, dense, interlocked, geologically stable, but it is fractured in others, worked over by 1,000,000 years of the Columbia River undercutting its banks. There are joints. There are hairline seams filled with secondary minerals, zeolites, calcite, that have healed old fractures. Probed with a handpick, the rock rings solid. Drilled, it produces competent core. No instrument available on site in 1934 can detect what those filled fractures will do under a sustained vertical load of 36 tons per axle. The construction railway system at Grand Coulee is one of the most extensive temporary rail operations in American history at that point. 12 miles of trackway at peak operation, 5 locomotives, 1,200 aggregate cars. The system moves concrete materials from the crushing plant on the north bank through a network of switch yards and along the canyon walls to the mixing plants positioned at various elevations above the dam's upstream face. It is a logistics operation of the first order. When the excavation crews cut down to foundation elevation, and the decision is made to extend the haul line directly onto the working face of the bedrock. The reasoning is simple. The concrete cannot wait for a longer haul road, and the basalt looks solid. No one tests it under load before the locomotive runs. This is not negligence. It is the edge of what anyone knows how to do in 1936. There is no standard protocol for dynamic load testing of bedrock in a construction setting. No portable instrumentation, no field procedure. What exists is the locomotive, the schedule, and an aggregate deficit of 10,000 cubic yards accumulating every day. The mixers sit idle. So the Baldwin rolls onto the exposed foundation surface on January 7th. It runs without incident for 38 hours. On the morning of January 9th at 5:53 a.m., it stops. The investigation takes 11 days. 2 engineers fly from the Bureau's Denver office to the site. A structural geologist from the U.S. A geological survey arrives by train from Spokane the following afternoon. Earl Cushman, who has not left the site in 36 hours by the time they arrive, briefs them at the track. What they observe is precise, and that precision is what makes it disturbing. The rail sections beneath the locomotive's driving wheel cluster have subsided uniformly. Not twisted, not buckled laterally, settled, plumb. The way a foundation pier settles into soft clay, except this is not clay. By every field measurement they have, this is competent basalt. The geologist calls for cores. He drills a grid of 6-inch boreholes around the subsided zone and maps what comes up. The cores from the upper 18 inches tell the story. The rock has not been crushed by the load. It has been elastically compressed along a system of sub-horizontal fractures spaced 2 to 4 inches apart through that upper stratum. Each fracture is healed, calcite-filled, appearing sound in any standard field test, but the calcite is softer than the basalt. Under sustained high load applied over a small bearing area, each healed fracture deflects a fraction of a millimeter. Stack 15 of those fractions, and you have 6.5 inches of settlement in a machine that has nowhere to go. The foreman's notation had it wrong in the best possible way. Rock does exactly this, once you understand what rock actually is. The fix is not fast. It cannot be. The locomotive is jacked off the subsided rails over 2 days, using 12 hydraulic jacks, rated at 100 tons each, borrowed from 2 other active sites on the project. The machine is moved laterally on temporary roller assemblies to a section of compacted fill-grade roadway south of the foundation zone. It will sit there for 5 weeks. In those 5 weeks, the engineering team redesigns the trackway for the entire exposed foundation zone. The solution is concrete pads, poured directly onto the bedrock surface, 12 inches thick, steel reinforced, spanning a bearing area 4 times wider than the original timber tie footprint. Rails are embedded in the pads during the pour. The distributed contact area between track structure and rock surface increases from roughly 8 square inches of effective bearing per axle position to 38 square inches. The math is not complicated. The load hasn't changed. The rock's capacity hasn't changed. What has changed is the area over which that load is spread. and 38 square inches of contact against 28,000 pounds per square inch basalt produces a bearing stress the rock handles without record. The Baldwin returns to service on February 17, 1936. It does not stop again. Over the next 6 years, this locomotive and 3 others like it move a quantity of construction material sufficient to pave a 2-lane highway from Seattle to Washington, D.C. They haul aggregate, form lumber, steel reinforcement, mechanical equipment. Near the end of the project, they haul the first of the generator stators, components built by General Electric and Westinghouse, weighing up to 87 tons each, from the rail siding at Coulee City down to the powerhouse excavation. By the time Grand Coulee pours its last concrete in December of 1942, the construction railway has accumulated over 2.2 million car miles of operation in some of the most demanding terrain and weather conditions in the American West. Not one of those car miles involves a second settlement event. What the January 9th incident produces beyond a repaired track and a resumed schedule is a protocol that will outlast everyone involved in creating it. The Bureau of Reclamation codifies its foundation load testing procedure in Technical Memorandum 638, published in March of 1937. The memo requires that any heavy equipment operating with an axle load above 50,000 pounds on exposed bedrock at a Bureau construction site must first pass a foundation assessment, cores taken and logged, horizontal fracture frequency documented, secondary mineral content classified, and a bearing capacity certification signed by a licensed engineer. The signing engineer is personally accountable. The certification is project record. The Army Corps of Engineers adapts this framework for its own construction standards in 1939. By the close of World War II, the protocol has spread across federal civil works construction in every region where water infrastructure is being built on rock. Every dam that follows, Shasta, Friant, Hungry Horse, Flaming Gorge, Glen Canyon, carries in its construction record a lineage that traces back to 12 hydraulic jacks on a frozen canyon floor in eastern Washington in the winter of 1936. Engineering learns most of what it knows from the moment something stops working. What matters is whether the lesson holds. Grand Coulee enters service on March 22, 1941. Its first 2 generating units come online at the 108 megawatts nameplate capacity each. The Columbia River, impounded behind a concrete structure 550 feet high and nearly a mile across the crest, begins moving through 18-foot diameter penstocks at a volume of 130,000 cubic feet per second. The power lines leaving the switchyard that spring run south to Boeing's manufacturing facilities in Seattle, which is about to begin producing B-17 bombers at a rate that will change the outcome of a war. Today, Grand Coulee operates 33 generating units. Its nameplate capacity is 6,809 megawatts, making it the largest single hydroelectric installation in the United States. In peak summer months, when snowmelt fills the Columbia and the Pacific Northwest grid pulls at maximum demand, a Grand Coulee alone can power the equivalent of 2.3 million homes continuously. Its pumping plants lift Columbia River water 280 feet up into the Banks Lake Equalizing Reservoir, from which 6.1 billion gallons per year flow by gravity into the Columbia Basin Project, 671,000 acres of eastern Washington that would otherwise be high desert. The project feeds wheat, potatoes, corn, alfalfa. It feeds cattle operations and dairies. It feeds a regional economy that did not exist before the dam. The total construction cost in 1942 dollars was $163 million. In comparative current value terms, adjusted for complexity, it would exceed $4.5 billion today. By any output to investment measure in the record of American public works, Grand Coulee remains in a category of one. The Baldwin locomotive that stopped its trains for 5 weeks in January of 1936 was scrapped in 1948. Its boiler went to a smelter in Tacoma. Some of its driving wheel sets were reportedly salvaged into a smaller yard engine working the grain elevators along the Snake River. No photograph of the machine taken during its Grand Coulee service years is known to have survived. The concrete pads it forced the engineers to design are still in the ground. They are beneath the dam's foundation now, encased in concrete, unlabeled, indistinguishable from the structure around them. They will be there as long as the dam is there, which is to say, they will be there longer than anything else anyone reading this will ever build. Earl Cushman retired from the Bureau of Reclamation in 1951. In his exit documentation, a personnel officer asked him to name the most significant project of his career. He named Grand Coulee without pause. When pressed on why, he said it was the only project where the problem that nearly stopped them was smaller than the answer it produced. He was talking about a locomotive. He was talking about fractured basalt. He was talking about the gap between what engineers assumed rock would do and what rock actually did. The dam kept going. The river kept moving. The West built itself around both of them. That is what infrastructure does. That is what it has always done. Under this video, there's a subscribe button. It's a small action, but it keeps stories like this moving. If you're drawn to the systems that operate quietly beneath America's coastlines, rivers, and reservoirs, subscribing simply means you want to see more of what flows beneath the surface. That's enough.